Hello, welcome to the third module of the Python Fundamentals course, which is about the structure and organization, or modularity, of Python programs. Modularity is an important property for anything but trivial software systems, as it gives us the power to make self-contained, reusable pieces which can be combined in new ways to solve different problems. As with most programming languages, the most fine-grained modularization facility is the definition of reusable functions. Collections of related functions are typically grouped into source code files called modules. Modules can be used from other modules, so long as we take care not to introduce a circular dependency. As we've seen already, we can import modules into the REPL, and we'll show you how modules can be executed directly as programs or scripts. Along the way, we'll investigate the Python execution model to ensure you have a good understanding of exactly when code is evaluated and executed. We'll round off by showing you how to use command line arguments to get basic configuration data into your program and make your program executable. To illustrate this module, we'll be taking the code snippet for retrieving words from a web-hosted text document we developed at the end of the previous session and organizing it into a fully fledged Python module. Let's start with the snippet we worked with last time. Open a text editor, preferably one with syntax highlighting support for Python, and configure it to insert 4 spaces per indent level when you press the Tab key. You should also check that your editor saves the file using the UTF-8 encoding, as that's what the Python 3 runtime expects by default. Let's get the snippet we wrote at the REPL at the end of the previous module into a text file called words.py. All Python source files use the .py extension. Now we're using a text file for our code, we can pay a little more attention to readability. Let's put a blank line after the import statement. Save the file in a directory called pyfund in your home directory. Switch to a console with your operating system shell prompt and change to the new pyfund directory. We can execute our module simply by calling Python 3 and passing the module's file name. When you press return, after a short delay you'll be returned to the system prompt. Not very impressive, but if you got no response, the program is running as expected. If on the other hand you got an error, an HTTP error indicates there's a network problem, while other types of error probably mean you mistyped the code. Let's add another for loop to the end of the program to print out 1 word per line. This is much better. Now we have the beginnings of a useful program. Our module can also be imported into the REPL. Let's try that and see what happens. Start the REPL and import your module. When importing, we omit the file extension. The code in your module is executed immediately when imported. Maybe not what you'd expected, and not very useful. To give us more control over when our code is executed, and to allow it to be reused, we'll need to put our code in a function. Let's quickly define a few functions at the REPL to get the idea. Functions are defined using the def keyword, followed by the function name, an argument list in parentheses, and a colon to start a new block. We use the return keyword to return a value from the function. As we've seen previously, we call functions by providing the actual arguments in parentheses, if there are any, after the function name. Functions aren't required to explicitly return a value though. Perhaps they produce side effects. You can return early from a function by using the return keyword with no parameter. A return keyword without a parameter, or the implicit return at the end of a function, actually causes the function to return none, although remember that the REPL doesn't display non-results, so we don't see them. By capturing the returned object into a named variable, we can test for none. Let's organize our words module using functions. We'll move all the code except the import statement into a function called fetchWords. You do that simply by adding the def statement and indenting the code below it by 1 extra level. Save the module and reload the module using a fresh Python REPL. The module imports, but the words are not fetched until we call the fetchWords function. Alternatively, we can import our specific function. So far so good, but what happens when we try to run our module directly from the operating system shell? Exit the REPL with Ctrl-D on Mac or Linux, or Ctrl-Z on Windows, and run Python 3, passing the module file name words.py. No words are printed. This is because all executing the module does now is define a function and then immediately exit. To make a module from which we can usefully import functions into the REPL, and which can be run as a script, we need to learn a new Python idiom. The Python runtime system defines some special variables and attributes, the names of which are delimited by double underscores. One such variable is called double_name, and gives us the means for our module to detect whether it has been run as a script or imported into another module or the REPL. To see how, add print__name at the end of your module, outside the fetchWords function. First of all, let's import the modified words module back into the REPL with import words. We can see that when imported, double_name does indeed evaluate to the module's name. As a brief aside, if we import the module again, the print statement will not be executed. Module code is only executed once on first import. Now let's try running the module as a script with Python 3 words.py. Now the special name variable is equal to the string main, which is also delimited by double underscores. Our module can use this behavior to detect how it is being used. We replace the print statement with an if statement which tests the value of double_name, and if it is equal to double_main, executes our function. Now we can safely import our module without unduly executing our function, and we can usefully run our function as a script. It's important to understand the Python execution model and precisely when function definitions and other important events occur when a module is imported or executed. Here we show execution of our Python module in the PyCharm graphical debugging environment. We step through the top-level statements in the module. What's important to realize here is that the def used for the fetchWords function isn't merely a declaration. It's actually a statement which, when used in sequence with the other top-level module scope code, causes the code within the function to be bound to the name of the function. When modules are imported or run, all of the top-level statements are run, and this is the means by which functions within the module namespace are defined. We're sometimes asked about the differences between Python modules, Python scripts, and Python programs. Any Py file constitutes a Python module, but as we have seen, modules can be written for convenient import, convenient execution, or, using the if name equals main idiom, both. We strongly recommend making even simple scripts importable, since it eases development and testing so much if you can access your code from the Python REPL. Likewise, even modules which are only ever meant to be imported in production settings benefit from having executable test code. For this reason, nearly all modules we create have this form of defining one or more importable functions with a PostScript to facilitate execution. Whether you consider a module to be a Python script or a Python program is a matter of context and usage. It's certainly wrong to consider Python to be merely a scripting tool in the vein of Windows batch files or Unix shell scripts, as many large and complex applications have been built exclusively with Python. Now we'll look at setting up a main function with a command line argument. We'll start by refining our word fetching module a little further. First, we'll perform a small refactoring and separate the word retrieval and collection on the one hand from the word printing on the other. This is because when importing, we'd rather get the words as a list, but when running directly, we'd prefer the words to be printed. Next, we'll extract a function from our if name equals main block called main. By moving this code into a function, we can test it from the REPL, which isn't possible while it's in the module scope if block. We can now try these functions from the REPL. We'll use this opportunity to introduce a couple of new forms of the import statement. The first new form imports multiple objects from a module using a comma-separated list. The parentheses are optional, but they do allow you to break this list over multiple lines if it gets long. This form is perhaps the most widely used form of the import statement. The second new form imports everything from a module using an asterisk wildcard. This latter form is recommended only for casual use at the REPL. It can wreak havoc in programs since what is imported is now potentially beyond your control, opening yourself up to namespace clashes at some future time. Having done this, we can fetch words from the URL, print any list of words, or indeed run the main program. Notice that the print words function isn't fussy about the type of items in the list. It's perfectly happy to print a list of numbers. So perhaps print words isn't the best name. In fact, the function doesn't mention lists either. It will happily print any collection that the for loop is capable of iterating over, such as a string. Given this, we'll perform a minor refactoring and rename this function to print items, changing the variable names within the function to suit. We'll talk more about the dynamic typing in Python which allows this degree of flexibility in the next module. One obvious improvement to our module would be to replace the hard-coded URL with a value we can pass in. Let's extract that value into an argument of the fetchWords function, called URL. When running our module as a standalone program, we need to accept the URL as a command line argument. Access to command line arguments in Python is through an attribute of the sys module called argv, which is a list of strings. To use it, we must import sys at the top of our program and then get the second argument with an index of 1 from the list. This works as expected when we pass a URL from the command line. This all looks fine until we realize that we can't usefully test the main function any longer from the REPL because it refers to sys.argv1, which is unlikely to have a useful value in that environment. The solution is to allow the argument list to be passed as a formal argument to the main function using sys.argv as the actual parameter in the if name equals main block. Testing from the REPL again, we show that main is also usable from here. For more sophisticated command line processing, we recommend you look at the Python standard library argparse module or the inspired third-party docopt module. You may have noticed that our top-level functions have two blank lines between them. This is conventional for modern Python code. Sparse is better than dense. 2 between functions. That is the number of lines PEP8 recommends. According to the PEP8 style guide, it's customary to use 2 blank lines between module-level functions. We find this convention has served us well, making code easier to navigate. Now we'll look at documenting your code using a feature called docstrings. We saw previously how it was possible to ask at the REPL for help on Python functions. Let's look at how to add this self-documenting capability to our own module. API documentation in Python uses a facility called docstrings. Docstrings are literal strings which occur as the first statement within a named block, such as a function or module. Let's document the fetchWords function. We use triple-quoted strings even for single-line docstrings because they can easily be expanded to add more detail later. One Python convention for docstrings is documented in PEP 257, although it's not widely adopted. Various tools such as Sphinx are available to build HTML documentation from Python docstrings, and each tool mandates its preferred docstring format. Our preference is to use the form presented in Google's Python style guide, since it is amenable to being machine parsed while still remaining readable at the console to humans. Now we've added the docstring, we can access it through help from the REPL. We'll go ahead and add similar docstrings for our other functions, print items, and main. Each docstring begins with a short description of the purpose of the function, followed by, as necessary, a list of the arguments to the function and the return value. Then we'll add one for the module itself. Module docstring should be placed at the beginning of the module before any statements. Now when we request help on the module as a whole, we get quite a lot of useful information. Next, we'll introduce Python code comments. We believe docstrings are the right place for most documentation in Python code. They explain how to consume the facilities your module provides rather than how it works. Ideally, your code should be clean enough that ancillary explanation is not required. Nevertheless, it's sometimes necessary to explain why a particular approach has been chosen or a particular technique used, and we can do that using Python comments. Comments in Python begin with a hash symbol and continue to the end of the line. Let's document the fact that it might not be immediately obvious why we're using sys.argv1 rather than sys.argv0. This is because the 0th argument of sys.argv is the module file name. And now the whole shebang. It's common on Unix-like systems to have the first line of a script include a special comment called a shebang. This begins with the usual hash as for any other comment, followed by an exclamation mark. The shebang allows the program loader to identify which interpreter should be used to run the program. Shebangs have an additional purpose of conveniently documenting at the top of a file whether the Python code therein is Python 2 or Python 3. The exact details of your shebang command depend on the location of Python on your system. Typical Python 3 shebangs use the Unix env program to locate Python 3 on your path environment variable, which importantly is compatible with Python virtual environments. The standard Python 3 shebang passes Python 3 to the user bin env program. Don't worry if you're on Windows, Python includes machinery to make this work on Windows too. On Mac or Linux, we must mark our script as executable using the chmod command before the shebang will have any effect. Having done that, we can now run our script directly. Since Python 3.3, Python on Windows also supports the use of the shebang to make Python scripts directly executable with the correct version of the Python interpreter, even to the extent that shebangs that look like they should only work on Unix-like systems will work as expected on Windows. This works because Windows Python distributions now use a program called PyLauncher. PyLauncher, the executable for which is simply py.exe, will parse the shebang and locate the appropriate version of Python on your system. For example, on Windows, in CMD shell, simply words.py followed by the URL as the command line argument will be sufficient to run your script with Python 3, even if you also have Python 2 installed. You can read more about PyLauncher on Windows in PEP 397.